Hello, I'm Thomas Viehmann. You might know me from the PyTorch forums or from the book I wrote with Luca Antega and Eli Stevens, Deep Learning with PyTorch, which you can download from the PyTorch webpage. I run a boutique PyTorch and machine learning consultancy, MudInf, from Munich. And today I want to talk to you about inspirations from going abroad. So we're going to look at running our PyTorch models elsewhere. And this might mean on mobile, to take a PyTorch-powered model with us on our phone. It might mean embedded hardware. Many people start with the Raspberry Pi as a model embedded hardware, but sometimes you need AI acceleration, so you have embedded or edge AI hardware, or you might get by with other embedded hardware. Or you might have new devices and backends that we might wish to offload computation to, which are not yet well supported by PyTorch. How do we go at getting PyTorch to run on these? Let's look. One option is to port PyTorch. So PyTorch on mobile phones became a thing in late 2018 with a full, when we had a proof of concept and there was a full PyTorch mobile presented at the DEF CON last year. This has lots of tailoring, glue code, custom builds to reduce size, and so on, and you need that for a good experience. This focuses on JIT models, and while it's running quite well, it's also still benefiting from improving efficiency on the mobile CPUs and GPUs. The other route, the easier route, is PyTorch on the Raspberry Pi. We get the full PyTorch because we can just compile PyTorch on the Raspberry, but you're advised to use 64-bit. And this is easy. You have the full PyTorch experience for the Raspberry this way. And we can also compare to other implementations available there, like Onyx Runtime or TVM, which we'll talk about in a bit, and look for optimization targets. So we might have the vision that PyTorch in itself is good enough for most purposes, just like you currently have as the status quo on GPUs, where PyTorch is reasonably fast, except if you need something very specific. Another route is to take the models and export them. And so here are two examples, Onyx Runtime from Microsoft and Apache TVM. So Onyx Runtime, you need to export your model to Onyx, obviously, and this is slightly more limited than the JIT in expression. But running on Onyx Runtime gives you good performance out of the box for many hardware, for example, on the Raspberry, but also on other hardware. And this is due to the optimizations that Onyx Runtime has seen. One thing about Onyx Runtime is they are fixed on using files as the means of exchange, with all the benefits and disadvantages that come from that. One thing we might ask for PyTorch is whether PyTorch should make the round trip possible, so should PyTorch take in Onyx? Moving to Apache TVM, this goes a little bit a different route. This will take in the PyTorch JIT graph, and the conversion from the PyTorch JIT graph and to the TVM model is implemented in Python. And there, one of the hard bits is getting the types of all the intermediate results exactly right. But then you can tune this for new hardware and optimization patterns, which is one of the purposes of Apache TVM, with great ease, and you have access to the latest and greatest of these automatic optimizations. So there's a third way that combines the best of both worlds, and that is to hook into PyTorch. And two popular examples are the Torch Vision library itself and also TR-Torch. So what they do is they provide a JIT extension, and this is necessarily in C++ at the moment. And so if you want, Torch Vision takes the easy part and does that. It registers custom ops in the PyTorch JIT. This allows to quickly bind third-party libraries too. For example, if you have a library that you want to benchmark PyTorch against, or you want a quick speed up because some library available on specific hardware is faster than PyTorch, then you can just wrap the ops you need. There also is a more advanced use that you can also fuse operations together, combine them in order to save writing intermediate results to memory. And for this, you need to rewrite the JIT graph in a custom pass. For example, TR-Torch does that, and so did the prototype of Torch TVM that existed for a while. The advantage to the user is that you stay in PyTorch and you have the full PyTorch experience, and at the same time you can cherry pick which things run externally. And so you can benefit from optimizations that PyTorch itself doesn't do yet out of the box. And in a way, this is also used in PyTorch itself, so the speedups we get from JITted models often are the result of fusing operators within PyTorch with the fusers that we developed. When we see these three approaches, and I've tried them all and invested quite a bit of time in making each one work for the things I wanted to do, you have some sort of ideas what could be done to PyTorch to make this even easier and to offer more opportunities. And so with the JIT at the center of all of this, a future might have a JIT that's even easier to use. We might supplement the current bottom-up approach of JITting, where you have to have all the functions you use in a scriptable or traceable way before you can JIT your model. We might supplement this by having a top-down use, where you start JITting your model, and if there's gaps that cannot be JITted yet, PyTorch will fall back to the Python. And in a way, if you have seen the functional transform FX module used in PyTorch quantization, this is a very similar idea that you can that you want to JIT only parts of the model, very specific parts, to work on these in transformations. And one thing this might enable, which would be a fairly large step forward in my mind, would be to have JITted by default modules. So currently, if you want to run a model on a different platform, you go and develop your model, then you JIT it, and then you can run it. But with JITted by default, you would have a very small, if not completely eliminated, second step. So you can easily just develop your model, and then you can run it on the hardware immediately without needing to work a lot on JITting your model. Furthermore, we might have things that makes it easier for developers to do creative things with the JIT. And so one thing would be Python implementable passes. In a way, the FX module seems to be an advertisement, and this might be a neat feature. And then there's the question, who does differentiation? PyTorch actually has two differentiation mechanisms, autodiff in the JIT and autograd, which we all know from PyTorch and from the regular use of PyTorch. And so to narrow this difference might be a good goal to have functions that work in autodiff, like in autograd, or also to make available backward operators for everything so you can compose things easier. We might also make more information available, like type and shape info for each operator. So this is being worked on in the context of static typing and symbolic info, but even the dynamic information would be useful. For example, when we export our model to something like TVM, getting the typing information from PyTorch would be a tremendous help. So these are ideas where we could improve the JIT for both the users and the developers and broaden the scope where it can be used. And this is my reflection on PyTorch when I return. I thank you for listening and watching, and I'll be available on the first networking session